We showed the location of two of the equilibrium points, the Lagrangian points L4 and L5. These are called the triangular Lagrangian points because they are located in the apex in the vertices of equilateral triangles opposite the base, which is formed by the line joining the two masses. We can show that there are actually three other Lagrangian points. These are called the collinear points because they lie in the line joining the two masses. These are the L1, L2, and L3 points. The L1 and L2 points are very close to the planet, and the L3 points in the opposite side of the orbit. Let's see how we can show that these are equilibrium points. We showed before that in the three-body problem, one of the constants of motion was a Jacobi constant, which is given by twice the quantity u minus the square of the velocity, where the quantity u is given by the coordinate system such that you are using x as the axis in the line joining the masses, and the origin is at the barycenter. We're going to use units such that the mean motion is equal to 1, and mu1 is g times the mass of the primary, mu2 is g times the mass of the secondary, and we're going to use units such that mu1 plus mu2 is equal to 1. And the separation between the masses, the semi-major axis of the two-body problem, is equal to 1. Therefore, the mean motion is also equal to 1. R1 is the distance from a test particle to the primary, and R2 is the distance from a test particle to the secondary. So imagine that you have a particle somewhere, and R1 is the distance to primary, and R2 is the distance to the secondary. We are looking for equilibrium solutions. That means that there is no motion. Therefore, to find these points, we can set v to be equal to 0. So the Jacobi constant is simply equal to twice the quantity u. So that makes it relatively simple to find out where these equilibrium points are. We take the derivatives on both sides, and because the Jacobi constant is a constant, this must be equal to 0. So the condition that we want to find is simply du dt is equal to 0. Now u depends on x and y, so du dt is equal to the partial derivative with respect to x and the partial derivative with respect to y. Now this should go to 0 independently, which is also seen from the equations of motion. The equations of motion in the co-rotating frame are the acceleration in x minus the Coriolis force is equal to du dx, and the acceleration in y plus the Coriolis force is equal to du dy. If we are in equilibrium, there are no velocities and no accelerations, so therefore these quantities must independently go to 0. So these are our conditions to find the equilibrium Lagrangian points. We need to solve du dx equals 0 and du dy equals 0 given the quantity u. So these are the coordinates of the problem. We have the star at the position minus mu2 and the planet at the position mu1. Mu1 plus mu2 is equal to 1. You can write the position of the particle r1 with respect to the sun as r1 squared is equal to x plus mu2 squared plus y squared, and r2 squared is equal to x minus mu1 squared plus y squared. So let's take these two equations here. Multiply the first one by mu1 and the second one by mu2. What you have then is, now if you sum both equations, then you have also expanding the squares. You can immediately see that the cross term is going to cut. So what you're left with is, now mu1 plus mu2 is equal to 1. And you can extract mu1, mu2 from these two terms, which will then give you mu1, mu2 times mu1 plus mu2, and mu1 plus mu2 is also equal to 1. So in the end, then you have isolate x squared plus y squared, and substitute this equation for x2 plus y2 into the equation for u. You end up with this different expression for u. Now you may be asking why we're doing this. We had an equation for u, and we are seemingly substituting that by an equation that is more complicated. But what's going on is that the previous equation was a function of x, y, r1, and r2, whereas this new equation is only a function of r1 and r2. So you substitute an equation that has 4 variables for an equation that has only 2 variables, so that the explicit dependence on xy is removed. The partial derivatives that we want to find, dux and dy, are much simpler than to find. Let's group together here the terms containing mu1 and the terms containing mu2, and the mixed term. The derivative of u with respect to x is then the derivative of u with respect to r1 and the derivative of r1 with respect to x, plus the derivative of u with respect to r2 and the derivative of r2 with respect to x. Similarly for y. These equations must be equal to 0. So let's take the derivative of u with respect to r1. The only term containing r1 is the first term, which gives you mu1 that multiplies minus r1 squared plus r1. Similarly, for the derivative of u with respect to r2 is mu2 minus 1 over r2 squared plus r2. We also have the equations for r1 and r2. Therefore, the derivative of r1 with respect to x, if we take the derivative of the first equation then with respect to x, we have 2r1 dr1 dx is equal to 2x plus mu2. So we cut the 2's on both sides and divide by r. And similarly, the derivative of r2 with respect to x is x minus mu1 over r2. And the derivative of both of them with respect to y is y over the radius. So we have the relations we need. Du with respect to r1, du with respect to r2, the derivatives of r with respect to x, and with respect to y. Let's use them for the equations that we need to solve. So making these substitutions, these are the equations that we end up with. Now looking at these equations, we immediately see that there is a trivial solution if these repeated terms, which are du dr, are equal to 0. So the first solution is canceling these first terms. So this happened for r1 equal 1 and also r2 equal 1. So that is the first solution, r1 equal to r2 equal 1. So for r1 and r2 to be equal to 1, these points must lie in the perpendicular bisector of the line joining the masses. And for both of them to be equal to 1, then what you have is an equilateral triangle, where r1 from the primary mass to L4, and r2 from the secondary mass to the point. And also, of course, on the other side of the orbit. So these are the triangular Lagrangian points L4 and L5. By convention, the L4 is the leading point and L5 is the trailing. You can see that indeed these are the triangular points by going again to the equations for R1 and R2 and substituting the fact that we found that both of them are equal to 1. So the equations to solve are x plus mu2 squared plus y squared equal 1 and x minus mu1 squared plus y squared equal 1. So the way to make this work is if x plus mu squared is equal to x minus mu squared, which will give you cut the x2 on both sides. Now mu1 plus mu2 is equal to 1. Now to get something that is mu1 plus mu2 here, you complete the square. So that this is mu1 squared plus twice mu2 squared, then minus 2 mu2 squared. Complete the square now, add twice of mu1 mu2 minus twice mu1 mu2. And then this gives you mu1 plus mu2 squared minus twice mu2 squared minus twice mu1 mu2. Now if you extract mu2 from these two terms, this is equal to mu2 squared minus twice mu2 of mu1 plus mu2. Now this is equal to 1 and this is also equal to 1. So what you have then is 1 minus twice of mu2 divided by 2 and you find the solution for x, half minus mu2. Now go back to the first equation and you solve this for y, x plus mu2, substitute x as half minus mu2, so you get rid of the mu2. This is half squared plus y squared is equal 1. The solution then is y is equal to plus or minus square root of 3 over 2, which you will recognize as the sine of 60 degrees. So the vertex of an equilateral triangle.